Good morning, everyone. Thank you all for being here today. It's my privilege to be a part of such a big community which is so much passionate about sharing knowledge and information. Before I dive into the good stuff, I want to run you through some basic standard who am I? And I promise this isn't me running who am I commands on my Windows terminal. I'm Amankumar Badhel, currently working as a threat researcher for Sophos Labs. I spend most of my times writing detections for various TTPs. When I'm not writing detections, I work on my calisthenics skills, paddling, and exploring the trails. So I think about it as hacking the outdoors, where I discover new paths, navigate the obstacles, and yes, I do debug my sense of direction. Today I'm going to take you on a journey of UAC and COM, where the secret sauce lies in the intersection of UAC and COM. And that's where the magic happens, followed by an exploit demo, as this talk is not just about the offensive side of COM-based UAC bypass. I'll be covering the monitoring and the detection aspects too, followed by Q&A. Let's dive in quickly to overview of UAC. What is UAC? UAC is basically a Windows security feature that forces all the process to run with the security context of limited privilege users by default. It's basically also a policy that applies to all the process which is created by any users, including administrators too. So the idea is to not solely rely on user's identity in order to determine the privilege activity which is being performed. In short, UAC thus prevents unauthorized changes. For example, it might seem very odd if Bob, being an administrator, downloads a malware without realizing it. Any process Bob would create would by default be created as an administrator. But what if UAC was turned off? In that case, malware would have got instant access to Bob's system. Whereas, what if UAC was turned on? Malware would have got limited privileges to Bob's system. Before I dive into the actual working of UAC, I would want to touch base on process integrity levels, tokens, and filter tokens. In Windows, there are 4 major process integrity levels: low, medium, high, and system. Low refers to minimal interactions, mostly used in Internet Explorer. Medium refers to standard privileges, which is being assigned to any normal users. High is then reserved for administrative users. Subject in this level can modify object at a lower integrity level as well as at the same integrity level. System is then reserved for kernel and core operating system processes. Tokens and filter tokens. In order to provide separation of roles, non-administrative users and administrative users are dealt separately. During the logon process, non-administrative users would receive only single token. This token is with medium integrity level and is used to perform all the operating tasks. Screenshot shows us how medium integrity token looks like in token viewer and in command prompt. Whereas administrative users are dealt differently. During the logon process, administrative users would receive 2 tokens. First, a filter token and an elevated token. Filter token is with stripped off privileges. It is referenced with medium integrity level and is used to perform all the normal operating tasks. Whereas elevated token has much more higher privileges as compared to the filter token, and it references higher integrity level and is used to perform only and only administrative tasks. As we have covered the basic understanding of UAC, let's dive deep into the actual working of UAC. When a user wants to run cmd.exe as an administrator, at the backend, shell execute function is then executed with the following argument of run as and cmd.exe. This request is then forwarded to application info services, where application manifest would verify if cmd.exe has auto elevation enabled by default. If not, then this request is then forwarded to consent.exe, where user gets a prompt for UAC on a secure desktop. Based on user's input, cmd.exe is then launched with a higher integrity level. Windows COM. It's a very dull and dry topic in my honest opinion. Anyone who has dwelt with Windows COM, I can assure you, anyone who has dwelt with Microsoft website for Windows COM, I can really assure you that it is designed to test two things. First, your patience. Second, your troubleshooting skills. Today I'm going to take you on a journey of Windows COM. This is going to be a very effortless journey, and I assure you that there won't be any tangling wires. Overview of COM. So basically, COM is a client-server module which allows inter-process communication. So think of it more comparable to an HTTP API. As shown in my figure, client, that is foo.exe, would initiate a request to create the COM object, which is referenced via specific unique ID called as GUID, also called as CLS ID. Windows COM that acts as a middle layer between the client and the COM object. It also verifies if the client request has appropriate privileges to access the COM object. If this request is authorized, Windows COM then creates the COM object and provides a reference back to the client. Once the reference is established, client can then access all the methods and the function available for the COM object. Any interaction that is happening back and forth between the client and the COM object happens via RPC in the case of COM, as well as in the case of distributed COM, where clients and servers are on a different machine altogether. Screenshot shows the registry location, where you can list down all the available COM objects into your system. Second screenshot is a very juicy aspect with respect to COM-based UAC bypass. This would be further explained in the intersection of UAC and COM. As we have had a basic understanding of COM interaction and UAC, let's try to unwind the secret sauce and dive deep into the intersection of UAC and COM. Certain COM interactions are designed to support automatic elevations by default. That means specific tasks within COM object can be executed with elevated privileges without prompting for a UAC. The only constraints are that client should be a system trusted binary or a Microsoft signed binary. This particular registry key is strictly managed by Windows in order to prevent any unauthorized modification. Over the wild, Black Cat and Logbit ransomwares were found to use these kind of COM-based UAC bypasses. Let's try to dive deep into the exploit flow. Attacker would execute the exploit, which is foo.exe in our case. Exploit would first spoof its process environment block to explorer.exe in order to impersonate itself as a system trusted binary. Exploit then uses a very specific COM object, which is referenced by the CLS ID in the screenshot. This COM object is from CMSTP Lua and has a very special shell execute method. This method is then used to run applications. Exploit then constructs an elevation moniker. Elevation moniker is a COM feature which would create the requested COM object with elevated context. System in our case, would just verify if the client is a system trusted binary. But exploit has spoofed its process environment block to explorer.exe in order to impersonate itself as a system trusted binary, which results in the creation of COM object with elevated context. Exploit then uses this particular object in order to use shell execute method and then launch cmd.exe with a higher integrity level without prompting for a UAC. Normally launching cmd.exe with a higher integrity level would prompt you for a UAC. But as in our case, shell execute method was executed via elevated COM object. It inherits the privileges of elevated COM object and spawns cmd.exe with a higher integrity level without prompting for a UAC at all. And it's time for an exploit demo. Someone did mention to me that before I run to the exploit demo, pray for the demo god. But as demo god is on Christmas vacation today, let's hope for the best and brace for the worst. So I have a low privilege shell running here, and I'm currently running on a medium integrity level. Verifying the privileges and integrity level via whoami commands, and then I'll be using this shell in order to launch my exploit. While executing my exploit, I'll be passing cmd.exe as an argument. Successful execution of the exploit would launch a new instance of cmd.exe with a higher integrity level without prompting for a UAC. And you can see that I have another shell which is currently running on a higher integrity level, much more privileges as compared to the previous one, and and that's all without prompting for a UAC. As we have covered the working of COM-based UAC bypass, I want to take this opportunity in order to discuss the detection aspects too. Since we know exploit uses COM object and dllhost.exe acts as a COM surrogate process where it also orchestrates the creation of COM object with elevated context, then any payload which is executed within the exploit via shell execute method is then spawned as a child process of this particular DLL host. In simpler terms, my detection logic would be monitoring for something like any child process which is created by dllhost.exe having parent process as dllhost.exe, whereas command line should have a COM object CLSID as a reference while excluding some system generic noises. Let's try to look at this logic in our detection tool. So I have a Python detection tool running in the backend, which is UAC bypass detection.py, and I have a low privilege shell which I'll be using in order to execute my exploit, verifying the privileges via whoami priv and passing cmd.exe as an argument for the exploit. Successful exploitation would launch a new instance of cmd.exe, and as you can see, I have a higher integrity shell, and at the back end you can see that I have a detection on my tool which spits out all the relevant information with respect to process, like child process being my cmd.exe, parent process being my dllhost.exe, whereas you can also see that I have COM object CLS ID as a reference in its command line. In order to wrap it up today, we have covered working of COM-based UAC bypass, its detection technique. With appropriate visibility, we can create sophisticated detections for any threats. Thank you all for your time, and I'm happy to take any questions. Last but not the least, thanks for my mentor Ali and my partner Vaishnavi.